Subscribe to Dr. Khalkar's classroom channel and press the bell icon to get latest updates. Hello everyone, I hope you are doing great. In my previous lecture video, I have discussed about basics of laser and its mechanism, characteristics of laser and levels of laser. In this lecture video, I am going to discuss about laser part 2. So let's get started. In this lecture, I'll discuss about semiconductor laser, carbon dioxide gas laser, and the applications of lasers in several fields. The science of laser is strongly related to types of conventional lasers such as solid state laser with size about few 10 centimeters, helium neon gas laser with size about 30 centimeters, ND-arc laser with size about 60 centimeters, CO2 gas laser with size about 100 centimeters, and lasers for satellite communication with size around 100 meter. The semiconductor laser is constructed by many parts like gain media, cavity mirrors, optical pumping module, and encapsulation case. However, the actual size of laser pointer is less than 10 cm. But if we take a look inside the laser pointer, most of the part is filled with battery. More precisely, size of laser diode is 1 mm. It is hard to fabricate such powerful tool with the size of 1 mm. Nowadays, it's possible with the help of nanotechnology and advanced fabrication techniques. Most important part of laser is gain media. The gain media of laser is semiconductor material. Most common semiconductor materials used in laser are gallium arsenide indium phosphorus for red color, gallium phosphorus for green color, and gallium nitrogen for blue color. Let's try to understand the physics behind the semiconductor laser. A semiconductor homojunction diode lasers are solid-state lasers based on semiconductor gain media, where optical gain is usually achieved by stimulated emission. It is usually fabricated by using p-type semiconductor over a n-type semiconductor. Then a depletion layer is formed, which is an active layer. The top and bottom faces have metal contacts to pass the current. The front and rear faces are polished to constitute the resonator. Laser light emission takes place at inner band transition under conditions of high carrier density in the conduction band. So as shown in this band diagram, the band diagram of heavily doped PN junction without bias is shown here, in which EV is energy level of valence band and EC is the energy level of conduction band. EF is Fermi energy level, whereas EG is energy gap between valence band and conduction band. When high doped P and N regions are joined at the atomic level to form PN junction, the equilibrium is attained only when the equalization of Fermi energy level takes place as shown here. Now let's see the working mechanism of semiconductor lasers. When the junction is forward biased, electrons and holes are injected into the junction region in high concentrations, as shown in figure A. In other words, Charge carriers are pumped by the DC voltage source. When the diode current reaches a threshold value, as shown in figure B, the carrier concentration is the junction region will rise to a very high value. As a result, the region small d contains a large concentration of electrons within the conduction band and simultaneously a large number of holes within the valence band. Thus, the upper energy level in the narrow region are having a high electron population while the lower energy levels in the same region are vacant. Therefore, the condition of population inversion is attained in the narrow junction region. This narrow zone in which population inversion occurs is called an inversion region or an active region. The recombination of electron and hole pairs lead to emission of spontaneous photons. The spontaneous photons propagating in the junction plane stimulate the conduction electrons to jump into the vacant states of valence band. This stimulated electron-hole recombination produces coherent radiation. For example, gallium arsenide laser emits light at a wavelength of 9000 angstrom in infrared region. This is all how the lasing action is happening in the semiconductor laser. Now let's see the next type of laser, that is CO2 gas laser. The CO2 gas laser is a molecular gas laser based on a gas mixture as the gain medium, which contains carbon dioxide, helium, nitrogen, and possibly some hydrogen, water vapor, or the xenon. Such a laser is electrically pumped via an electrical gas discharge, which can be operated with DC current, with AC current, for example 20 to 50 kHz, or in the radio frequency, that is RF domain. It is a 4-level molecular laser and operates at 10.6 micrometer in far infrared region. The CO2 gas laser is capable of continuous output powers above 10 kilowatt. It is also capable of extremely high power pulse operation. Let's see the construction of CO2 gas laser. This laser is a gas discharge quartz tube of about 1.5 mm square cross section and 260 mm length. A water cooling system is connected to tube to maintain the temperature. A DC current with AC current, example 20 to 50 kHz, or the radio frequency RF power supply is connected to the tube. Tube is filled with mixture of CO2 gas, N2 gas, and the helium gas in ratio 1:4:5. The ratio can be varied depending on application of laser. The two mirrors arranged externally, one is fully reflective and other is partially transmissive, forms the optical resonator. Back and ground ends of quartz tube are fully reflected and partially reflected respectively to get laser output. Atoms are excited by AC or DC electrical discharge. The CO2 molecules are active centers where N2 atoms helps CO2 molecules in achieving population inversion. Now let's try to understand how energy is transferred amongst gas molecules. It is depend on vibrational modes. Let's try to understand the vibrational modes in molecule. Radiation in the infrared IR region of electromagnetic spectrum has the energy to excite vibrations of covalent bonds. The absorption of IR radiation causes bonds to stretch and bend. Stretches correspond to the increasing and decreasing of the bond lengths within a molecule. Bends corresponds to increasing and decreasing the angle between bonds in a molecule. The animation below show the possible vibrations of the CO2 molecule. There are 3 vibrations: symmetrical stretching, asymmetrical stretching, and symmetrical bending. All 3 vibrations require different amounts of energy, so the CO2 molecule absorbs IR radiation at three different wavelengths. Although each CO bond in CO2 is polar, its linear shape means that the molecule as a whole does not possess a dipole moment. During the asymmetrical stretch and bend, the symmetry is lost and a dipole is momentarily created. It is possible to excite these two vibrations with IR region. During the symmetric stretch, however, no dipole moment is created and so IR radiation is unable to excite this vibration. CO2 thus absorbs at only two wavelengths in the IR. These vibrational degree of freedom are quantized. At any one time, a CO2 molecule can vibrate in linear combination of these vibrational modes. The figures below show the possible vibrations of the CO2 molecule in diagrammatical form. The energy states of the molecule are represented by three quantum numbers m, n, and q. These numbers represent the amount of energy associated with each mode. For example, the number 0 to 0 indicates the molecule in this energy state is in pure bending mode with 2 units of energy. Each vibrational state is associated with the rotational states corresponding to the rotation of CO2 molecule about its center of mass. The separation between vibrational rotational states are much smaller on the energy scale compared to the separations between electron energy levels. The N2 molecule is also characterized by similar vibrational levels. So these two diagrams shows vibrational mode as well as the rotational mode. Now let's see the working mechanism of CO2 gas laser with the help of energy level diagram. In this diagram, the lowest vibrational levels of the ground electron energy state of CO2 molecule and an N2 molecule. The excited state of N2 molecule is metastable state and it is identical in energy to 001 vibrational level of CO2 molecule, which indicated as E5 in this figure. So let's see the pumping mechanism. When current passes through the mixture of gases, the N2 molecule gets excited to the metastable state. The excited N2 molecules cannot spontaneously lose their energy and consequently the number of N2 molecules at the metastable state level builds up. The N2 molecules undergo inelastic collisions with ground state CO2 molecules and excite them to E5 level. Some of CO2 molecules are also excited to the upper level E5 through collisions with electrons. The E5 level is the upper lasing level while the 0 to 0 and 100 states marked as E3 and E4 levels acts as the lower lasing levels. As the population of CO2 molecules builds up at E5 levels, population inversion is achieved between E5 level and the levels at E4 and E3. Random photons are emitted spontaneously by a few of atoms at the energy level E5. The spontaneous photons traveling through the gas mixture prompt stimulated emission of photons. The photons bounce back and forth between the end mirrors, causing more and more stimulated emission during each passage. The strength of stimulated photons traveling along the axis of the optical cavity, that is the discharge tube, builds up rapidly while the photons traveling at angles to the axis are lost. The laser transition between E5 to E4 levels produces far infrared radiation at the wavelength of 10.6 micrometer. The lasing transition between E5 to E3 levels produces far infrared radiation at 9.6 micrometer wavelengths. E3 and E4 levels are also metastable states and the CO2 molecules at these levels fall to the lower level E2 through inelastic collisions with the normal or unexcited CO2 molecules. This process leads to accumulation of population at E2 level as the gaseous mixture heats up The E2 level, which is close to the ground state, tends to be populated through thermal excitations. Thus, the de-excitation of CO2 molecules at the lower lasing level poses a problem and inhibits the laser action. The helium atoms de-excite CO2 molecules through inelastic collisions and decrease the population density of CO2 at E2 level. It is also aids cooling the gaseous mixture through heat conduction. The CO2 molecules are once again available for excitation to higher state and participate in lasing action. CO2 molecules are excited to the upper lasing level continuously through the collisions. As the population inversion can be maintained in the face of continuous laser emission, the laser operates in continuous wave mode. This is all about the CO2 gas laser. Now let's see the actual CO2 gas laser, a CO2 gas laser demonstration in which the glow running through the center of the tube is an electric discharge. This glowing plasma is the gain medium for the laser. The laser produces a tiny intense spot on the screen to the right. The center of the spot appears white because the image is overexposed there. Lasers plays very important role in the holography. So let's see one of application of laser, that is the holography. Holography is used to project objects shown in some movies. Here are some clips and some laser shows. A hologram is a physical recording of an interference pattern which uses diffraction to reproduce a three-dimensional light field, resulting in an image which retains the depth, parallax, and other properties of the original scene. So in these pictures, you can see the 3D light fields in movie clips, as well as here is a one in laser show, a elephant picture which shown with the help of holography. There are two important stages in the holography. First is a recording of hologram and second one is a reconstruction of image. So let's see these two one by one. The recording of hologram is based on the phenomena of interference. It requires a laser source, a plane mirror, beam splitter, an object, and a photographic plate. A laser beam from the laser source is incident on plane mirror or beam splitter. One part of a splitted beam, after reflection from the beam splitter, strikes on the photographic plate. This beam is called a reference beam, while other part of splitted beam, that is transmitted from the beam splitter, strikes on the photographic plate after suffering reflection from the various points of object. This beam is called object beam. The object beam reflected from the object interferes with the reference beam when both the beams reach the photographic plate. The superposition of these two beams produces an interference pattern in the form of dark and bright fringes, and thus this pattern is recorded on the photographic plate. The photographic plate with recorded interference pattern is called hologram. The actual experimental setup of holography is shown in this picture. The arrangement of several mirrors and beam splitters gives us the holography reconstruction of the images in three-dimensional form. Now let's see the reconstruction of image. In the reconstruction process, the hologram is illuminated by laser beam, and this beam is called a reconstruction beam. This beam is identical to reference beam used in the construction of hologram. The hologram acts a diffraction grating. This reconstruction beam will undergo phenomena of diffraction during the passage through a hologram. The reconstruction beam after passing through the hologram produces a real as well as a virtual image of object as shown here in this diagram. Here is one important application of holography is demonstration of some images in three-dimensional form, which is used in teaching. So the appearance of virtual image in three-dimensional forms gives more detailed information about the image. Now let's see the scientific applications of the laser. In science, the lasers are used in many ways, including a wide variety of interferometric techniques, Raman spectroscopy, laser-induced breakdown spectroscopy, atmospheric remote sensing, investigating nonlinear optics phenomena, holographic techniques employing lasers also contributed to a number of measurement techniques. Laser-based LIDAR technology has application in geology, seismology, remote sensing, and atmospheric physics. In astronomy, lasers have been used to create artificial laser guide stars used as reference objects for adaptive optics telescopes and satellite communications. Lasers are also used in other applications such as optical disk drives, laser printers, QR or barcode scanner, DNA sequencing, optical fiber communication, photolithography to fabricate semiconducting devices, free space optical communication, surgery and skin treatment, welding and cutting of materials, military and enforcement, measuring speed and temperature, and entertainment. This is all about semiconductor laser, CO2 gas laser, applications of lasers. In next lecture video, I will explain about optic fiber, that is next topic. So please do not miss my next video. Thank you. Below this video, in the description, the link of important information related to this video is given. Please go through it. Please like and share this video and subscribe to Dr. Khalkar's Classroom channel to get the notifications about my upcoming videos. Thank you.